Hello everyone, I'm Himanshu Vasnani from Department of Mechanical Engineering and I'm here to discuss you on the subject non-destructive evaluation and testing. Subject code is ME419, unit number 5, lecture number 36 in the series. Today's topic are inspection of fastener holes and prop design in ECI. ECI is Eddy Current Inspection. Okay, the drilling objective for today's are to provide the students with a basic understanding of inspection of fastener holes and to know about prop design in eddy current inspection. And learning outcome after today's lecture will be the students will have an understanding of inspection of fastener holes and students will understand prop design in ECI. Now, we have been discussing about eddy current inspection in the past lectures. Okay, and we know that this non-destructive technique is very effective in testing of you can say material thickness also. So let's check about metal thickness measurements. So you can see that a wide range of thicknesses can be measured with low frequency eddy current equipments. Okay, now let's discuss about low frequency eddy currents. Now, low frequency eddy current means the inspection requires frequency below 50 kilohertz. What they say? The inspection it requires frequencies below 50 kilohertz. So, improved equipment and data processing techniques now allow the use of test frequencies as low as 55 hertz. Okay. Now, along with the impedance plane equipment to measure signal phase, this has provided a means for testing multi-layer thick materials. Okay. Now, the detection of deep subsurface cracks, cracking in intermediate layers of material and corrosion on the backside of a material is possible. Now, when we're talking about low frequency eddy currents, they say that the low frequency eddy current means that the inspection is requires frequencies that is below 50 kilohertz. Okay, but nowadays in today's world we have improved equipments and data processing techniques now, and they allow the use of test frequencies as low as 50 hertz. Okay, so you can so so much advancement has been done till now. Okay, so detection of deep surface cracks, cracks in you can say cracking in intermediate layers of material and corrosion on the backside of a material, it is possible. Okay, it is possible to know that also. Now, dual frequency testing. Now, this is a basic version of multi-frequency testing. What? This is a basic version of multi-frequency testing that can be used to filter out one undesired condition. Okay, if two frequencies are used, so one frequency channel can operate in the differential probe mode. Okay, what they say, if two frequencies are used, one frequency channel can operate in the differential probe mode. Okay, and the other frequency channel can operate in the absolute mode. Okay, so you can filter out okay the conditions. Now with this setup, the differential mode can be used to detect discrete indications such as small cracks and holes. This differential mode, this can help you to detect small holes or small cracks there. And the absolute mode can be used simultaneously to record wall thickness of or other dimensional changes in the test part. So you can see this dual frequency testing is very helpful. Okay, it is giving you multi frequency testing. It is filtering, helping you to filtering out. Okay, like you can use both the modes simultaneously, like differential probe mode and absolute mode also. Okay, so let's go to the further. Now, electromagnetic techniques closely related to eddy currents. Now, although not part of the eddy current testing as currently defined, the following are the most closely related to eddy current testing rather than any other basic NDT methods, like Backerson noise testing of ferromagnetic materials. Now, abnormal stresses induced by short peening or the cold working. Peening means that hitting with a hammer. The short peening, other cold working processes and grinding burns affect the structural properties of a material. Okay, and can lead to flaw growth and part failure also. So in ferromantic materials, these processes affect the ease with which the magnetic domains in the surface of the material can be moved. Okay. Now, in unmagnetized ferromagnetic materials, the magnetic domains are randomly and if the material is subjected to a magnetic field, the magnetic domains tend to align themselves in the direction of the magnetic field. If we give a magnetic field to this kind of material, like unmagnetized ferromagnetic material, the magnetic domains, it will align themselves in the direction of magnetic field. Now, when the domains tend to align themselves, the electric pulses are generated during the domain movement, and this is called as Barkhason noise. And this electrical noise can be detected and measured by Hall effect sensor. Okay, this electrical noise, this can be detected and measured by Hall effect sensor. And if the material is free of abnormal stresses, the domains are relatively free to move, and little Parkinson noise is generated. So areas of tensile stress parallel to the applied magnetic field causes an increase in Parkinson noise. What they say? Areas of tensile stress parallel to the applied magnetic field causes an increase in the Parkinson noise. So examples of applications of this test method are ferromagnetic engine component and landing gears. So Parkinson noise measurements are also used to detect the quality of drilling and reaming of holes in ferromagnetic materials. Okay, now magneto optic imaging (MOI), short form is MOI. Now, magneto-optic imaging, it depends on the ability of certain materials to rotate the plane of polarization of light in the presence of a magnetic field. Now, this Faraday effect is used to detect disturbances. What is this? This Faraday effect is used to detect disturbances in the magnetic field produced by passing an alternating current in a thin planar foil of doped deuterium iron garnet. Now, when the foil is placed in near the surface of a metallic test object, the eddy currents are produced, which modify the magnetic field in the foil. Once say the eddy currents, these are produced which modify the magnetic field in the foil. So when defects or other material discontinuities such as rivets or holes, these divert the otherwise uniform flow of electric current near the surface of the test piece. So magnetic fields perpendicular to the surface of the test piece are produced, which can be imaged in real time by an appropriately designed optical system. So since the system provides optical information, the results can be videotaped for analysis and permanent documentation. In this way, magneto-optic imaging can be. Now, application of advanced techniques, like several of the advanced techniques and processes discussed above, do not have fully developed and recognized test procedures, such as controls and the qualification procedures. Now, specific applications of all these processes and techniques shall be in accordance with the approved procedures and engineering approval. So these all things are under development. Okay, so these require some specific applications on which they are applicable. Okay. Now, the general applications of eddy current testing. They say that all inspections for cracks and other in-service flaws should be considered critical. So each inspection on every aircraft or weapon system should be approached with utmost care and concentration. Now always set up your eddy current instrument in accordance with the established procedures. Be sure to check your setup several times during the inspection to ensure our equipment is responding properly. See, this is a thumb rule for every inspection that we should always make sure that the setup is complete for inspection, because if any you can say setup is missing, or if there is any minute kind of establishment is problematic, then obviously the response or the response signals will not come properly. So in order to have the response properly, we should check our setup that it is you can say complete the during the inspection of the material. Okay, yeah, your equipment is completely set up during the inspection of the material. Now take time to ensure that you have carefully scanned the entire area of inspection, double checking your scans if necessary. Okay, now this the inspection can perform maybe the last line of defense against the possible failure due to the crack growth. Okay, now, not finding a defect in an area during a previous inspection does not discount the odds of it presenting itself in the future. Okay, if you have made an inspection in the past, that doesn't mean that this time also you can't find a defect. So approach each inspection as if it was there was a known flaw in the area you are inspecting. So inspect like you are there is a flaw, so that you can do your work generously. Now, some terms that we should consider. Well, thinking of the eddy current testing, like null point. Now, the null point is a location or an impedance plane at which the eddy current instrument is nulled or zeroed. Okay, if nulled correctly on a defect-free material, the instrument will place that signal dot on a specific point on the display. And any changes in the material, such as crack, will cause the signal dot to reflect an electrical impedance change on the display. This is how the null point is helpful. Okay, so the parameters, and there are a large number of parameters that can be set up on an adequate instrument. So, however, the parameters most often adjusted by technicians are frequency, gain, phase angle, sensitivity, and filters. Okay, so see, the parameters are also important because in order to analyze the data, in order to analyze the readings that we are getting, so certain these parameters should also be counted, should also be, you can say, seen, because should also be studied. Okay, now let's talk about frequency now. So the only freely adjustable parameter on modern instruments that affects the eddy current is frequency. So the rest of the parameters are all they are only to enhance the visibility of the signal response on the instrument. You see, the rest of the parameters, okay, apart from frequency, the rest of the parameters are there only to enhance the visibility of the signal response on the instrument. See, now the lower the frequency, the deeper the field goes into the material. The lower the frequency, the deeper the field goes into the material, and therefore the increased depth at which the eddy current flows. So for frequency, you can just simply say that the only freely adjustable parameter on modern instruments affect the eddy current is frequency. Okay. Now gain. Okay, gain is also a very important parameter that we should consider. Okay, the gain can be increased to get a larger signal response, that is to make a small signal more visible. Okay, or decreased to lower the signal response on an instrument display. Now, however, increase in gain will increase the noise on the instrument display, and noise can be caused by a variety of factors like the electronics of the instrument, okay, and material noise resulting from grain structure of the material noise caused by the mechanically altering the surface of the material under test, okay. So noise can be formed by various factors. Or if you increase in grain, will increase the noise on the instrument display panel also. So some instruments feature H gain or V gain, okay. And H gain stands for X squared and V gain stands for Y squared along the regular gains. So these two gains allow the operator to independently increase or decrease the signal in the vertical or horizontal direction. This these two gains will allow the operator these two gains, H gain and V gain, these two gains allow the operator to independently operate. You can independently increase or decrease the signal in the vertical or horizontal direction and are very useful for helping distinguish noise signals from flow responses. Okay, now what to say that these gains, these will, if you increase in gain, then obviously you will increase the noise on the instrument display, and the noise can be from various factors. So what happens that we have there's some instruments have the H and V gain. So these two gains, H and V gains, these allow the operator to independently increase or decrease the signal in the vertical or horizontal direction. Okay, and are very useful for helping to distinguish noise signals from the flow responses. Now, phase angle is also an important parameter. Okay, let's go with it. That may be also known as the rotation or the rotation angle. So, unrelated to the true phase of the eddy current, it is a setting that allows the user to rotate the signal response on the instrument screen. Okay, okay, this is a setting that allows the user to rotate the signal response on the instrument screen. So it may be used to orient the signal or response from the lifting the probe of the material, lifting lift-off signal when using an absolute probe. And this aid the user in distinguishing between the lift-off and a signal likely caused by a flaw. Sensitivity. Sensitivity is also a very important parameter. They say that the sensitivity is a parameter that allows for magnification of the instrument display. Okay, it's a parameter that allows magnification of the instrument display. It acts like a zoom feature of the camera, and it does not improve the image. It only makes it larger or smaller. Okay, now it is used to set the scale of the grid shown on the display. So common setting is like 1 volt per scale division. This means that a signal that is two scale divisions had two divisions long has a voltage of 2 volts. That's simple. The display is there on the screen. Now the grid is on the screen on the display. Then this measure is used to classify signals as acceptable or rejectable. Okay, so though the sensitivity is not available on all instruments, that is the first thing. So it depends upon the instrument. It is having that parameter feature or not. Now filters. Now filters is also very important because when you are testing there are various kinds of you can say signals are coming. So you need to filter that's what we want. So the used to filter out unwanted signals and improve the signal to noise ratio. Okay. Then three types of filters can be used like high pass, low pass, and band pass. And a high pass filter, that is HPF, it removes low frequency signals and lets high frequency, you can say frequency pass, and is useful to eliminate the effect of gradual variations in conductivity or dimensions on the eddy current response. And a low pass filter, that is LPF, it removes high frequency signals and lets low frequency signals pass and can be used to overcome electronic noise from harmonic frequency due to variation in magnetic permeability. Okay, so there's the difference between high pass filter and low pass filter. See, the high pass filter, as the name says, it removes low frequency signals and lets only high frequencies pass. Okay, so it is useful to eliminate the effect of gradual variations in conductivity or dimensions on the electronic form. Let's talk about low pass filter. Okay, that is the LPF. So LPF says it removes high frequency signals and lets only low frequency signals to pass. And this can be used to overcome electronic noise from harmonic frequencies due to variation in magnetic permeability. Now the third one, the band pass filter, it combines low and high pass filters to allow a response over a specific range of frequencies and suppress frequencies above and below this range. So these three filters are used, and these filters obviously are, you can say, filter out the unwanted signals and improve the signal to noise ratio. Now the modulation analysis. Now a technique useful in separating signals of interest from other signals relies on analysis of, you can say, signals as a function of time. Now, a good example of this is they're using a sweep display or a strip chart where the amplitude of the signal appears on the vertical axis and the times at which the signal appears and disappears is monitored on the horizontal. So, an example of modulation analysis is when a CRT is used in the sweep mode. Now, during the rotating bolt hole inspection, for the say, an example of modulation analysis is when the CRT is used in the sweep mode during the rotating bolt mode inspection. So in this technique, the equipment is typically set to each trace across the sweep represents one rotation in the hole. So here in the sweep mode, what they are doing example of modulation analysis is when the CRT is used in the sweep mode during the rotating bolt hole inspection. Okay, now what that happens, the clock position of an indication in the hole can be determined by its location across the sweep. Of more importance is the width of the indication and how long it deviates from the baseline. So in this example, how long the indication is detected, that is the width, okay, and is used to identify whether or not it is due a variable of interest. Okay, and for example, out of roundness in a bowl hole will produce an indication that lasts a long period, while a crack is very narrow and produces an indication that lasts a short period. So there is a difference between a bolt hole and a crack. Now, the bolt indications may have the same amplitude, but perhaps only the crack is of interest. So an electronic filter can be used to suppress long-lasting signals at a frequency, leaving only the crack indication, that is high frequency, on the display for the inspector to view. So in this way, you can understand that you can differentiate between a bolt hole or you can differentiate between a crack. Okay, so you can understand that out of roundness, a bolt hole it will produce an indication that will last for longer period. Okay, while the crack is very low, is very narrow, and obviously it will produce an indication that will lasting for a short period. So here, what we'll do, our interest is to find the crack. Okay, our interest is not find the hole, bolt hole. We need to find out the crack first. So the crack is the for interest. So we can see to use a filter that we just studied in the previous slide. to suppress the long-lasting signals, that is low frequency, leaving only the crack indication, high frequency, on the display for the inspector to view. So in this way, we go for modulation analysis. Okay. Now frequency response. Okay. So they say that frequency response analysis is the most common form of modulation analysis. Now during eddy current testing, the impedance of the test coil remains constant, provided there is no change in the inspection conditions or material properties. Now, when variations in impedance do occur, the rates of change in the impedance and resultant eddy current signal are proportional to the rates at which material properties are changing and the scanning field. Okay, when variations in impedance do occur, the rates of change in the impedance and resultant eddy current, the signals are proportional to the rates at which material properties are changing and the scanning speed. So consequently, a small crack would provide a rapid change in the impedance. A small crack would provide a rapid change in impedance during scanning and a corresponding high frequency eddy current signal. Okay, well these signals, these can be viewed on a video display or a strip chart recorder as a function of time. Now this is having you can say an application. Okay, what are they again? Then you can see that a small crack would provide a rapid change in impedance during scanning and a corresponding high frequency and signal. And you can view these signals on video display or a strip chart as a function of time. Okay, so this is really interesting. Now the effect on amplitude while encountering different kinds of material variations and scanning at a constant speed is shown in this figure. You can see in the figure on the right hand side. They say that the effect of material on magnitude of alternating current test coil with constant scanning speed. So in the first diagram on the upper side, you can see there's the amplitude on the vertical axis and time on the horizontal axis. They say that there is no change in the inspection material, so because of these signals. Okay, in the second diagram, you can see that there is slow change in inspection material. Okay, there you can see in the middle side how its variations are coming. So there is slow change in the inspection material. And in the third diagram on the bottom side, you can see that there is a rapid change in inspection material. So due to the variation is very for a very short time. So there is a rapid change in the inspection material. So through these material variables also we can understand how the alterations are being done. So fast signal change is often a good indicator of a small flaw and an abrupt change in material characteristics. So a slow signal change usually indicates a gradual change in dimensions, liftoff, or some other property. So frequency response is also a very you can say analysis technique and is one of the most common form of modulation analysis. Okay, so this is how it works. Yeah, the same diagram is again with you that I just discussed in the previous slide for you to discuss. Now, the inspection of fastener holes. Now, the cracks in fastener hole walls. When we a common application of eddy current inspection in aircraft structure is the detection of cracks in fastener holes or walls. Now, these cracks are usually generated by fatigue or stress corrosion or a combination of fatigue and corrosion. And the progress of these cracks is often slow in the initial stage, where early detection can prevail, possibly catastrophic failure. Okay, what happened? The progress of these cracks this is slow. In the initial stage, where early detection can prevent possibly catastrophic failure. So this is how uh, the inspection is done. Now the fatigue cracks. Let's discuss about all these cracks that are found. So the fatigue cracks, these are usually caused by repeated cyclic loading of a structure at lower stress levels than required for visible deformation. What do you call a fatigue crack? You can see that fatigue cracks these are usually caused by repeated cyclic loading of a structure at lower stress levels than required for visible deformation. Because stress is concentrated at areas of localized weakness such as holes or fatigue cracks often initiate at such points. Okay, so the cracks usually propagate normal to the direction of the maximum applied tensile stress. Okay, what they happen because stress is concentrated at areas at localized weaknesses. such as holes or fatigue cracks, often initiate at such points. So the cracks they usually propagate normal to the direction of maximum applied tensile stress. So the following is describe two types of fatigue, that is high cycle fatigue HCF and second is low cycle fatigue LCF. So in HCF, they say that usually means the stress applied is low compared to the ultimate tensile strength of the material. HCF means high cycle fatigue means it usually means the stress is applied low compared to the ultimate tensile strength of the material, but subjected to a very high number of cycles. Okay, example vibration or rate turbulence stresses. And we talk about LCF, that is low cycle fatigue. They say that LCF usually means stress is applied high compared to the ultimate tensile strength of the material, but subjected to a very low number of cycles, like takeoff or landing stress. Okay, so these two types of fatigue you can see that are discussed right now. Now the stress corrosion cracks. Now the stress corrosion cracks often occur this under a combined influence of a tensile stress and a corrosive environment on a material susceptible to stress corrosion cracks. What happens in this? They occur, these stress corrosion cracks they occur under the combined influence of a tensile stress. What they say? Combined. The stress corrosion cracks they occur under the combined influence of tensile stress and corrosive environment on a material susceptible to stress corrosion cracking. So the tensile stress may result from either an applied stress or a residual stress. The tensile stress that they are taking, tensile stress, it may result from either an applied stress or residual stress. And moisture in the air combined with the sufficiently corrosive environment may create stress corrosion cracking in some instances. So, see, the stress is coming. It is the stress is, may result from either an applied stress or residual stress. So this should be controlled. And in addition, a combination of cyclic fatigue in the presence of corrosion cracks can cause rapid growth of the cracks. This is also needs to be considered. Now, whole wall finish and dimensions. Now, the whole wall finish and the dimensions will influence both the occurrence and detectability of cracks in the fastener. What is there? The whole wall finish and the dimensions will influence both the occurrence and the activity of cracks in the fastener holes. Now, whole wall damage such as scratches or chatter and grooves created during manufacturing can create additional stress concentrations at the whole wall and provide preferred sites for crack initiation. Now, loose fittings bolts caused by oversized or out of round holes allow the movement in the area of the hole and allow fatigue action. Okay, these same conditions can influence the reliability of inspection, obviously. Now, during inspection, the severe damage to the whole wall results in eddy current indications and may not be separable from crack indications. So, excessive lift-off from the round-off conditions also mask indications from crack. All of these conditions can be created during manufacturing processes on the whole or as a result of fatigue action during servicing and from bolt removal. So these things should also be considered, okay, because this influence both the occurrence and the detectability of cracks in the fastener holes. Now the edge effects, okay, the edge effects are also very important. Now many cracks in the fastener holes this occur at or near the edge of the hole. So adjoining, you can say structures, non-uniform countersink and beavering radii and damage at the edge at the hole edges. Okay, increase the background noise. Okay, the factors that we discussed, this increase the background noise and decrease the signal to noise ratio. Now this leads to a general loss of detection of cracks at the edges of the holes, obviously. So further effects on the crack detectability result from the presence of other metals adjacent to the hole edges. So countersunk surfaces also limit the ET by manual techniques adjacent to hole edges. So in this way, the edges also affect. Okay, edges also affect the detection of crack. Okay, now the bolt hole preparation. Now holes in meeting surfaces must be realized prior to the ET or drilled to a larger diameter which is concentric to the meeting parts. Now, prior to performing bolt hole inspection, all foreign materials must be removed. Okay, from prior to performing this bolt hole inspection, all foreign materials must be removed from the hole. So foreign materials can include sealant, lubricant, metal slivers, and paint chips. Okay, what they say? These foreign materials, this can include sealant, lubricant, metal slivers, and paint chips. Usually, this material can be removed by using cotton swabs. This material can be removed by using cotton swab or a suitable solvent. Okay, you have to remove all foreign materials from the hole. Now, holes which are severely damaged during service or during fastener insertion removal may require reaming prior to use. So, if reaming is required, contact appropriate cognizant engineer for components for an approved method. Because see, whatever you are changes you are doing that requires the permission or you can say consideration of an engineer for further processing. Now, manual bolt hole scanning. Okay. So when used, manual scanning of bolt holes is performed at specified levels throughout the depth of the hole. Inspection is usually initiated with the center of the probe coil positioned immediately within the upper or lower edge of the hole, so that the outside edge of the coil is even with the surface of the part. What they say, then this inspection usually initiated with the center of the probe coil positioned. Okay, this inspection is usually initiated with the center of the probe coil positioned immediately within the upper or lower edge of the hole, so that the outside edge of the coil is even with the surface of the part. Now the probe coil position is adjusted to the specified level below the collar of the probe, and the probe is inserted into the hole until the probe collar rests against the surface of the part. Now occasionally the intergranular surface corrosion as IGC can occur along roughly parallel to the part surface. The indications from this type of corrosion appear similar to an elliptical shape hole or a slow change in activity. Okay, so in applications of band pass filtering may mask the presence of IGC. IGC is intergranular stress corrosion. So the important thing is that the one of thing that the inspection is usually initiated at the center of the probe coil that is positioned immediately within the upper or lower edge of the hole so that the outside edge of the coil is even and with the surface of the part. So in this way, you adjust the probe coil position and you obviously find out the thing, just do the scanning obviously. The automated bolt hole scanning. The automatic scanning is typically used for bolt hole inspection due to the increased detection capability over manual scanning. So this equipment provides a handheld scanning unit which drives a probe in the helical pattern through the length of the hole or rotates the probe at high revolutions per minute. So at a constant speed while the operator indexes the probe through the hole. Now equipment that rotates the probe in a helical pattern. What they say, these equipments that rotate the probe in a helical pattern is referred to as translational rotational scanner. What they say, the equipment that rotates the probe in a helical pattern is referred to as translational rotation scanner. And oftentimes, high-speed scanners do not have automated translational movement, and they depend on the rate at which the operator pushes and pulls the probe into and out of the hole. So results can be retained on a strip chart recorder or displayed on a digital display. Now the rotary scanner. Now this you can see the how in the diagram also you have the scanners. So they say that the scanner spins the bolt hole probe at a certain speed that has been on the instrument during setup. So the probe should be inserted into the fastener hole and indexed down the hole at a slow enough speed where the coil in the probe will scan the entire wall surface of the hole in a tight spiral, thus ensuring 100% surface coverage. What they do, the probe should be inserted into the fastener hole and indexed down the hole at a slow speed. Okay, at a slow enough speed where the coil in the probe will scan the entire wall surface of the hole in a tight spiral. Thus ensure 100% surface coverage. Okay, so in this way you can see in the diagram also that proper technique to ensure 100% coverage, that is on the left hand side you can see, and incomplete coverage you can see on the right hand side in the diagram. Okay. But how they have covered the 100% coverage and how the incomplete coverage is there on the right hand side. The same diagram is here. Now the rotary bolt probes, and you can discuss about that. Now the most common bolt hole probe design is shown in this figure. You can see that how the probe is shown. Okay, you have a coil at the left hand side, then the working length is there with you. That is, which is the shaft or the shank you can call it. Then there is a probe shell coming, and you have a O-ring in the there on the right hand side. Now the probe consists of this consists of a probe shell with a 4-pin connector and a main probe body. What they say? This probe it consists of a probe shell with a 4-pin connector and a main probe body. The shell features two O-rings, okay, and that holds and center the probe in the connector receptacle of the scanner. And the body consists of a shank with an integrated ball at the end called a head. So the shaft is split. Okay, you can see in the starting. The shaft is split, and one of the two halves of the head contains the sensor coil. Now, the split head provides spring compliance to ensure that the sensor coil can be as close to the wall of the fastener hole as possible. What they say? The split head it provides spring compliance to ensure that the sensor coil can be as close as the wall of the fastener hole as possible. So, when choosing a bolt hole probe, the diameter of the ball should be the same diameter or slightly smaller than the fastener hole. Okay, slightly smaller than a fastener hole to be inspected. So this provides the best fit once the shank is spread and the tape is applied. So this is a small working of a rotary bolt hole probe. Okay, and this is interesting. Obviously, this is very really interesting how this is done. Okay, okay, a rotary bolt hole probes. This is the same the diagram again. Now there are a variety of other designs such as probes with conical or cylindrical shaped heads or no heads at all. So, however, studies have shown that the ball-shaped probe provides optimum flaw detective throughout the fastener hole. What they say? That ball-shaped probe it provides optimum flaw detection throughout the fastener hole, including at the edges of both ends open. Now, this is really interesting. Okay, this is, I think, a very interesting thing that this ball shaped probe is giving you a good detectability. So the ball shaped probe obviously is giving you optimum flaw detectability for the fastener hole, which is really good, including the edges of the both open ends. So the ball shape helps to ensure that the coil is in contact with the fastener wall, even the probe is not quite aligned with the fix in the axis of the hole. Now you can for the typical coil configuration in a bolt hole probe. And the coil consists of two receiver coils, okay, each of which is wound on a D-shaped ferrite, okay, and receiver coils are then placed side by side and a driver coil is wound around both. So you can see that it is the diagram also is given that driver coil is there, receiver coil 2 is there. You have receiver coil 1 there with its ferrite is also there. So in this way they give you this configuration of the bolt hole probe. And the receivers are connected in difference. Okay, the difference this means that if receiver coil 1 sees something is causes an upward signal response, and if receiver coil 2 on the opposite side it sees something it causes a downward signal response. So this type of coil is called as differential reflection. Very effective of you can say giving you good detectability, good flaw detectability. Okay, throughout the fastener holes. Very good. Now this is a simple diagram that we just see. Now in this figure also you can see that on the right hand side this shows a typical bolt hole probe with a standard D50 differential reflection coil. Okay, and the A figure on the left hand side, and you can see that in the A figure you have this receiver coils inside and the driver coil is also there. Now the driver coil is the outermost coil and the driver coil generates an alternating magnetic field. The driver coil you can see in the diagram, this is the outermost coil and the driver coil generates an alternating magnetic field and penetrates the conductive material. Now the material reacts by generating eddy currents whose field opposes the primary electromagnetic field. Now since the incoming magnetic field is spread out, the That is, the effective field has a much larger effective area than just the coil diameter. The eddy currents are spread out. Okay, in this way they spread out. Now you can see in this figure on the right hand side, the figure B, it shows the eddy current distribution for the probe. Okay. Now the eddy current flow in the same circular pattern as the driver coil windings. Our strongest flows, what they say, these eddy currents it flow in the same circular pattern as the driver coil windings. Are strongest close to the coil windings and are slowly dissipate in the conductive material. Now how these are dissipating in the conductive material. So you can see the figure shows the outward extent and depth of the current to the point where the strength has reached 37% of the strength of the at the surface. Okay, you can see this is the standard depth of penetration that we discussed in the previous lectures. So you can see that how the setup is given. Okay. Now in this example, the result is that in an aluminum component of 200 kilovolts, a probe with a 0.07 diameter driver coil. Okay, you have an aluminum component at 200 kilohertz and the probe with a certain diameter driver coil will generate an eddy current about 0.08 inches deep into the material and will have a sensing area extending approximately of this much in diameter, which is really interesting. Okay, you can see the same diagram that we discussed in the previous slide. Now profit. Okay, profit is also very important. Profit is also really an important issue to be discussed. Now profit that fits properly within the hole is critical to inspection performance obviously. The poorly fitted probe will chatter in the hole resulting in excessive liftoff and signal noise. Okay, so the probe should be properly fitted within the hole. Okay, because if you want to do the good inspection, otherwise there will be signal noise. Now the following is the must procedure to ensure good probe fit. That measure the bolt hole diameter if you don't know it. Okay, measure the bolt hole diameter if you do not know it. Then select a probe with a size range that fits the bolt hole. Select a probe, select a probe with a size range that fits the bolt probe. Tape the probe, not insert it in the scanner, insert it into the hole. And if the probe can almost stand in the hole if the hole is vertical or hang inside the hole, okay, or not slip out of the hole, okay, and if you can still smoothly spin it by hand, the probe fit is correct. Okay, what they say, if the probe can almost stand in the hole if the hole is vertical and down, or hang inside the hole if the hole is vertical enough, or not slip out of the hole if the hole is horizontal. And if you can still smoothly spin it by hand, the probe fits it correct. Okay. Now, if the fit is not correct, then some non-conductive foam or rubbery material, okay, non-conductive foam or rubbery material into the slit in the shank of the probe and try again. That follow. So probe fit is obviously important because if the probe fit is proper, then obviously the inspection performance will be good. And if it is not proper, then obviously there will be excessive lift off and signal noise. Okay, so the better is to get a proper probe fit for better inspection performance. Okay. Now probe taping is also important. Okay. Now both bolt hole probes are manufactured using several types of materials depending on the probe type and manufacture. Now some probes are more durable than others. Okay, the probes made of soft plastics can wear and expose the coil windings in only few uses. Therefore, it is always wise to carry a spare probe. Okay, it is always wise to carry a spare probe. One way to protect the coil is to use a Teflon tape to cover the coil. Okay, now you can see that these probes are made up of soft plastics and obviously they can wear and expose the coil windings in a few uses. So it is always advisable to carry a spare prop and one way to protect the coil is to use a Teflon tape to cover the coil. Now part of how long a probe lasts and what responses you observe during inspection is how you tape your probe. So in the figure you can see in the upper figure it shows you examples of acceptably taped bolt hole probes. How they can easily acceptable. Okay. And then on the bottom side, you can see that there is unacceptable taping that it is incomplete. And also on both the figure on the bottom side, you can see that they both are showing unacceptable taping. Okay, the one is incomplete, the other is wrinkled. So you can see in the figure on the upper side, it shows an example of an acceptable taped probe. And an example, the tape smoothly covers the like a coil half of the probe without wrinkles, and the ends of the tape are tucked in between the split. Now in the bottom figures, bottom two figures, they show the examples of unacceptable tapings. Now the first figure that is on the bottom side shows tape covering with only the half of the coil, which would allow the edges of the tape to come up during the probe rotation in the coil. And the second figure on the bottom side it shows tape was not smoothly applied and it's wrinkled. Okay. Now probe alignment is also good because see probe is very important when you talk about ECI eddy current inspection. So when inspecting a hole, the probe must be guided into the hole such that the axis of the probe is aligned with the axis of the hole. Okay, you can see in the diagram also how the proper probe alignment is. How the second view on the right hand side is showing you the incorrect probe alignment. So you can see that while inspecting a hole, the probe must be guided into the hole so that the axis of the probe is aligned with the axis of the hole. Okay, so this may be difficult to do. Why? Because see, probe alignment is really important. And if you are having a bolt hole, so just make sure that while inspecting a hole, the probe must be guided into the hole such that the axis of the probe is aligned with the axis of the hole. And especially while monitoring the instrument screen at the same time. Okay. So if the probe is not properly aligned, the coil may not touch the bolt hole surface, preventing an effective inspection. So the probe may also wobble or chatter, causing excessive noise. So you should understand that you should go for correct probe alignment as shown in the first figure on the left hand side. So let's start with the MCQs now. Okay, the MCQ is also very important. Okay, right. The first MCQ is there in unmagnetized ferromagnetic materials. The magnetic domains are randomly oriented. So if the material is subjected to a magnetic field, the material domain, magnetic domains tend to align themselves in the direction of the magnetic field. So what do you think is true or false? So I think it's true in this case. Okay, so the answer is true. Now the null point is a location on an impedance lane at which the eddy current instrument is null or zero. So if the null is null correctly on a defective material, the instrument will place a signal dot on the specific point on a display, and any changes in the material such as scratch will cause the signal dot to reflect in electrical impedance changes on the display. So what do you think about this? We have discussed about this null point in our discussion also. So there is a null point is a location on an impedance at which the eddy current instrument is null or zero. So if the null correctly on a defective material, the instrument will place the signal or dot. What they say? If null correctly the defective material, then if on a defective material, the instrument will place a signal dot on a specific point on a display. Okay, now this line is very interesting. Okay, about the property of the null point, the parameter null point. Now, if the null correctly on a defective material, the instrument will place signal dot on a specific point on the display, and any changes in the material such as crack. Now comes the change in the crack will cause the signal dot to reflect an electrical impedance change on the display. This is true. Now gains can be increased to get a larger signal response, that is to make a small signal more visible, or decreased to lower the signal response on the instrument display. So however, increased gain will increase the noise on the instrument display. I think it's true. Now filters are used to filter out unwanted signals and improve the signal to noise ratio. True. A high pass filter improves low frequency signals and lets high frequencies pass and is used to eliminate the effect of gradual variations in connectivity or dimensions on the eddy current response. It's true. Low pass filter improves high frequency signals, sorry, it removes high frequency signals and lets low frequency signals pass and can be used to overcome electronic noise from harmonic frequencies and related to variations in magnetic permeability. So I think it's true in this case. Now the band pass filter, okay, it combines low and high pass filters to allow a response over the specific range of frequencies and suppress frequencies above and below this range. So this is also true in this case. Now common application of Eddy current inspection is the aircraft structures, that is the detection of cracks in the fastener holes or walls. So these cracks are usually generated by fatigue or stress corrosion or a combination of fatigue or corrosion. So the progress of these cracks is often slow in the initial stage, where early detection can prevent possible catastrophic failure. Okay, so this is such a kind of inspection, you can say, application. So they say that a common application of medical inspection in aircraft structures is the detection of cracks in fastener holes or walls. So these cracks are usually generated by fatigue or stress corrosion or a combination of fatigue. Okay, what they say, these cracks are usually generated by fatigue. So this is really important. These cracks are usually generated by a fatigue, stress corrosion, or a combination of fatigue and corrosion. The progress of these cracks is often slow in the initial stage, and the early detection can prevent possible catastrophic failure. So, what do you think? Is it true or false? Because see, in aircraft structures, these kind of cracks in fasteners holes is there. So that is why the application of eddy current inspection is more when you talk about aircraft structures. Okay, so if you go for the ECI, Eddy Current Inspection in aircraft structures, you can say that the application of detection of cracks and fastener holes or walls is very important. And these cracks, these are generated by either fatigue or stress corrosion or a combination of fatigue and corrosion. Okay, so if you find out these cracks in the early stage only, then obviously it can prevent some catastrophic failure. Okay, so it is true in this case, true. Now, fatigue cracks are usually caused by repeated cyclic loading of a structure at lower stress levels than required for visible deformation. What they say? Fatigue cracks these are usually caused by repeated cyclic loading of a structure at lower stress levels than required for visible deformation. Because stress is concentrated at areas of localized weaknesses such as holes or fatigue cracks, where often initiate at such points. The cracks usually propagate normal to the direction of the maximum applied tensile stress. So I think it's true in this case. Okay, because we know that the stress is concentrated at areas of localized weakness such as holes or fatigue cracks, and often initiate at such point. It is true in this case. True is the answer. A. Now, automatic scanning is typically used for bolt hole inspection due to increased detection capability over manual scanning. And this equipment provides a handheld scanning unit which drives a probe in a helical pattern through the length of the hole or rotates the probe at high revolutions per minute at a constant speed while the operator indexes the probe through the hole. So I think it's true in this case. The answer is true. So these are the references which you can refer and increase your knowledge in this topic. Okay. So these topics are very important when you talk about etiquette inspection. So try to refer these references and have a good upgrade in the knowledge.